Hi friends, let us today understand how to analyze an interpolator, or let us see how in Z domain or in omega domain interpolator actually looks like. So we have again something called as upsampler and something called as interpolator. Now we need to really understand what is the basic difference between these two guys. Now an upsampler is, let's say I give input as x of n and output as y of m, okay, then I upsample by a factor of, let's say, I, okay, then here I have fx and here I will have fy, which is I times of f of y will be equal to I times of f of x, okay, so in an upsampler I will just insert L minus 1 zeros and I will obtain the upsampling without taking care that if I upsample the signal, then there will be images in the spectrum, because when I am going to upsample the signal, that is I am increasing the sampling rate, what is going to happen? That the frequency characteristics are going on compressing. So increasing the sampling rate decreases the frequency spectrum or compresses the frequency spectrum. So when I am compressing the frequency spectrum, what is going to happen is in the same limit, now I am going to see more number of pass bands which are not desired. We desire only one pass band. I am just watching one movie again and again in different time instances or in different frequency instances. It's like that. So you are only very much interested into the information that you have been transmitted rather than getting the images of the information. It does not actually deliberately gives you any information. It is just the replication of the original information. So what I do is I will do upsampling, and because of upsampling we are going to get images, and instead of watching that images and processing that images, we will remove the images. To remove the images from the frequency domain, we will use filters. So an interpolator will be a system in which I will upsample the signal by, let's say, a factor of I, but then to remove the images we will use a low pass filter, which is h of n. So then I will get y of m output here. Okay, so what is happening over here? I am giving x of n as an input. Let's say this is my v of n. Okay, so what will be v of n doing here? V of n will be equal to now x of n by I. Okay, because I will be only picking up the integer factors, and then I am going to filter out, and v of n is equal to y of m, or we can say that y of m will be equal to convolution of h of n minus over k, h of n minus k into v of k. So I will be doing convolution of h of n minus k into v of k, and I am going to get y of m. But remember that v of n and y of m are one and the same. They are working on the same factors or same sampling rate. But x of n and v of n are not on the same sampling rate, but they are at different sampling rates. Here I have increased the sampling rate. Okay. So in an interpolator I will have an upsampler along with its filter, whereas in upsampler I will just upsample the sequence. Okay. How did we get this relation? Let us see that also. If I have here my x of n as a function of n, and I again draw a random sequence. Okay, I am very much interested into the time instances, so let us write the time instances. I have 5 time instances. I am going to upsample and I am going to achieve v of n. Now when I am going to upsample, what I will be doing is I will be inserting zeros. How many zeros? L minus 1 zeros. So for that, or I minus 1 zeros, for that I need to consider some I. So let's say I am interpolating by a factor of 2 therefore I minus 1 will be equal to 1. So I'll be pushing 1 0 at a time. Okay, so what I'm going to do, 0 will be there as it is. Okay, then I'll be putting a, at 1 I will be putting a 0. Then I'm going to get the next sample. Then I will push a 0. Then I'm going to get a next sample. Then I'm pushing a 0. Then next sample. Then a 0. Okay. So now here my, let's say here this is M. So M is going from 0, 1, 2, 3, 4, 5, 6, 7 and so on and so forth. Whereas N is running as, here it is 0. Okay, and where is 1? This was 1. Okay, so N is expanded compared to M. M is smaller. Okay, so what we can write here is V of, let's say, N is equal to X of N by I, and N will take 0 plus minus I plus minus 2I and so on so far factors. That is the integer multiples of I only will be present as a non-zero element in X of N. That means you can see here 0, 2, 4, 6 and so on and so forth. Okay, so this is 0 where N is equal to 0. Then here my N is equal to 2. Okay, sorry, N is equal to 1, I is equal to 2. Here N is equal to 2, I is equal to 2. So 4. Here N is equal to 3, I is equal to 2. So the value is 6. Okay, so I will have the expansion such a way that N will carry all the integer multiples of I. So that is nothing but the relation. This is very important again for the derivation sake. Okay, now let us directly start the derivation of interpolation instead of going. So in interpolation what we will be deriving is, we will be deriving what is going to happen at this point, that is at V of N, and then what is going to happen at Y of M. So I will be first deriving what is going to happen at this point, and then we will be deriving what is going to happen at this point. So we need to actually design this filter also. We need to actually understand what should be the characteristics of this filter also. Okay, so to go about in interpolation, the first step I will write is V of M, let's say, is equal to X of M by I, where M is equal to 0 plus minus I plus minus 2I and so on and so forth. Okay, and is 0 otherwise. Okay, so my V of M will have non-zero values at 0 plus minus I plus minus 2I and will be 0 otherwise. Okay, if I take the Z transform, so taking Z transform of V of M will give me V of Z. V of Z will be equal to summation N going from, let's say M going from minus infinity to plus infinity, V of M Z raised to minus M. Correct? Now what I am going to do is, I am going to substitute the value of V of Z equals to M going from minus infinity to plus infinity, and we know that it is X of M by I. Let's say I'll increase one more step, Z minus Z. Now what is happening is, only for M by I factors will be having non-zero values. Rest everywhere it will be 0 in the given summation. So what I can do is, I know that this factor is only valid in for integer multiples of I. Okay, or it is non-zero at integer multiples of I. So we can substitute something like this, M by I equals to, let's say, N. Okay, so I can have this to be going on N now, N going from minus infinity to plus infinity. Okay, X of N Z raised to minus, okay, N by N into I. Okay, now what is the definition of Z transform? So now I have I'll rewrite the equation. N goes from minus infinity to plus infinity, x of n z raised to minus n I. Correct? So, what I'll do is, I'll readjust the terms for z to get it in the form of z transform. I'll write it like this: z raised to I, the whole raised to minus n. Okay. Now, just to recall, x of z is equal to summation n going from minus infinity to plus infinity, x of n z raised to minus n. Correct? Right. So, in place of z, now I have z raised to I. So, now we have z raised to I in place of z raised to n. So, what I will do is, I will just replace, instead of x of z, I will write the new variable. So, I will get this as x of z raised to I. So, what is v of z? V of z is nothing but x of z raised to I. Now, how much part we have so far got is, like, we had a interpolator to which I have given input as x of n, which was upsampled by a factor of I, and then now I got v of m, let's say. Okay, and we know that this is my fx and this is my fy, okay, and which is equal to fx by I. Okay, now what I am going to do is, we will just observe what v of z will look like. Suppose in a frequency domain where I put as omega, let's say my signal is from minus pi to pi. The frequency components in the signal is from minus pi to pi. This is x of e raised to j omega x. Okay. So, the magnitude response of x of e raised to j omega x, the signal is given like this. Okay. Now, what I do is, I do the interpolation. When I do the interpolation, what is going to happen is, the same spectrum in omega will be reduced. Okay, it is going to get reduced from minus pi by I to plus pi upon I. Okay, and then at minus 2 pi by I to plus 2 pi by I, there will be a replication. Okay, and this is going to happen for infinite duration. Now, if suppose I have a system which looks for minus pi to plus pi, okay, which is somewhere now outside this boundary. So, what is going to happen is, in that point, or if I say that if this would be minus pi and this would be plus pi, then now I am going to get some extra values of the spectrum, which is again an unwanted one. So, what I'll do, I'll design a filter. So, what should be the filter look like? Now, this signal which I have drawn is an interpolator. So, this is magnitude of v of e raised to j omega y, which is x raised to x of e raised to j omega x omega y times of L. Okay, yeah, that will come as omega x by or you can say omega y by I. No, omega y times of I. That is correct. Omega x by yeah, that is right. So which is nothing but which is equal to this. I can write it as right here, v of e raised to j omega y has somehow comes to an x e raised to j omega y times of I. Okay, omega y times of I, that is z raised to I we got, right? So omega y times of I. that we have achieved. So yes, that is correct. Okay, because we are just substituting in place of z, I will put the value of e raised to j. Okay, now we know that because it has got this type of a characteristics, I wanted to suppress whatever is going out of this because it is one and the same. Okay, so what I wanted is, I want a filter to just give me this response. Its passband should be from minus pi by I to plus pi by I, and after that it should be in the, it is a stop band. So let us say that it's an ideal filter. So after v of e raised to j omega or after v of m, we are inserting a filter. So ideally the filter should have the characteristics as, I write in frequency domain, let's say some amplitude, because there will be some amplitude over here. So I said some amplitude c constant, I don't know what is the amplitude. For mod omega less than equal to pi by I, or minus pi by I to plus pi by I, and is 0 otherwise. Okay, this otherwise you can also skip and write mod omega greater than pi by I, mod 2 pi, that is understood. Okay, so we want a filter to be designed which will be of this form. Okay, so what will be the output? So when I say this is the upsampler, I gave input as x of, let's say x of z, I got your output as y of z, and I have the impulse, this is I, this is my h of z, and I am going to get your y of z. What will be y of z according to the convolution property? It will be v of z into h of z. Correct. So y of z will be equal to, okay, v of z into h of z. But now v of z is not, h of z does not exist everywhere. So it exists in some part. So of course y of z will also exist in some part. Okay, so instead of writing z, we replace z by e raised to j omega y now, because everything is in terms of omega y. Okay, and I will write y of e raised to j omega y, or just omega y, some books refer like that. H of e raised to j omega is c, okay, and v of z is x of z, which I can write as x of e raised to j omega y into l, omega y into I, for mod omega less than equal to pi by 4 and 0 otherwise, because in the rest of the part h z goes 0. Okay, so this is my y of e raised to j omega y. Okay, now the main task is to find what is the c is equal to. Okay, so to get what is c equals to, what I'll consider is, if I take inverse Fourier transform, okay, of, if I take inverse discrete time Fourier transform of this signal, I am going to achieve y of, let's say, m, which is equal to 1 over 2 pi dtft I am taking, minus pi to pi, or you can say 0 to 2 pi, y of e raised to j omega y, okay, d omega y. Oh, there is one more factor, e raised to, here it will be plus, yeah, it will be plus j omega y and m. Okay, so this is the definition of IDTFT. I have just written the, I have just written it later, but this should come like this: y of e raised to j omega y into e raised to j omega y m into d of, that is with respect to d omega y. I am writing d omega y because here the sampling rate is at omega y. Okay, the frequency, discrete frequency is at omega y. Okay, so what will be if I put m is equal to 0 in the above equation? I will get y of 0, which is nothing but 1 over 2 pi. Integral goes from minus pi to pi. Y of e raised to j omega y, which we will just put shortly. Then I am putting m is equal to 0, so I am going to get e raised to 0 d omega y. Correct? Now what is y of e raised to j omega y? It is nothing but c times of x of e raised to j omega y into e raised to j omega y I, this is z raised to I, into d omega y. So we cannot proceed further, so let us we will change the variable. So let us change the variable and bring everything in terms of x. So we know that omega y is equal to omega x by I. Okay, therefore if we differentiate on both sides, this will be d omega y equals to 1 over I d omega x. Correct? Let us substitute into the above equation and we will get y of 0 to be equal to 1 over 2 pi. Integral goes from minus pi to pi c. Okay, I will be getting x of e raised to j omega y. In place of omega y, I am going to put omega x by I into I. Okay, omega x by I into I, and in place of d omega y by d omega y, I will be putting d omega x with the I in the division. That is because of the change of variable. Now pulling out the constants, 1 over 2 pi into c over I, integral goes from minus pi to pi, x of e raised to j omega x, d omega x, right? So if I put c over I over in this place and I put 1 over 2 pi integral minus pi to pi, I'll write it very differently now, e raised to j omega x into, I can write it like this because there's nothing, I'll write it like this, e raised to 0 d omega x, and this e raised to 0 I can relate it like this, e raised to j omega x into n. Okay, and what is n in this case? Omega x cannot be 0. If it is 0, then this will also be e raised to 0. Okay, but it is not 0. It is some value. Okay, but n can be 0. Correct? So what does this total factor replicates? This total factor replicates the IDTFT formula for x of 0. Okay, so now I am going to get y of 0 equals to c over I, the whole thing I replaced by x of 0. Okay, now if I want to reconstruct the signal faithfully, then my y of 0 should be equal to x of 0, isn't it? That means the output should give me back what I have fed input. It should not restrict me. This is ideal situation. We are considering ideal situation. And for ideal situation, for y of 0 to be equal to x of 0, c must be equal to I. So what should be the highest peak of the transfer function of an interpolator is, now I can write h of omega y to be equal to, instead of c I will write as I, for mod omega less than equal to pi by I, and 0. So the transfer function of the filter is I, and mod of omega is 1 over I. So you can generalize and you can write the sequence as in general, you can write the sequence, that's not an issue. Let us write one more in terms of time instances. So in terms of time instances, I can write as y of m to be equal to, in general if I write y of m equals to, we can write it is nothing but the convolution of h of m minus k into v of k. Okay, and we know that v of k only exists at ki instant. Okay, so this convolution will be valid at k is equal to minus infinity to plus infinity. I can write as h of m minus k into, I can write it as x of k by n by I, you can write, that's not a problem. I'll write in terms of m by I, so write k, so k by I factors. Okay, and then if you replace it, change of variable, the convolution will convert into, sorry, k goes from, let's say, putting the same variable, k is equal k. I am now going to get h of m minus ki into x of. So this is the output of an interpolator. So again, in interpolator, we had our upsampler first, and then the transfer and then the low pass filter to remove the images. And due to insertion of a low pass filter, now the output, the new output is y of m, which is upsampled. But the sequence is given as h of m minus ki into x of k. So the transfer function of the filter looks like a multiples of I. Okay. Now, even though the filtering is linear, that means the low pass filter that I have used in interpolator or decimator is linear, the overall process of decimation and interpolation is time variant. So, even though we do the filtering as invariant process, the total decimation and interpolation processes are time variant. Thank you.